Hello, everybody. I hope you're doing well. Welcome back to the series on reviewing your probability and statistics fundamentals. Today, we're going to be discussing the idea of random variables. But before we jump into that, let's jump into some basic stuff on mean, variance, and standard deviation of a data set. So, suppose I have a data set of numbers. So, I'm going to just kind of give some random input. So, let's say 1, 2, 2, 4, 4, 4, 5, right? So suppose this is my data set, right? And what do I want to find in this data set? When you have data, we need to come up with a way to investigate it, right? Which means we want to have some numbers or some way of summarizing our data set to understand it. Well, here's a way of summarizing this data. We could simply plot a histogram, right? So we say for number one, how many such occurrences there are. So I'm going to put number of occurrences on my y-axis, and I'm going to basically put the value of the data set on the x-axis. So value. So the values you get are 1, 2, 3, 4, 5. So we see for value 1, right, only one time it occurs. For data set 2, it occurs twice. For data set 4, it occurs 3 times. For data point 5, it occurs 1 time, right? So this is keeping track of the frequency, right? And through the shape of the distribution, we could sort of see kind of how our data is distributed, right? So one question to ask yourself is, do you think this data set's a little imbalanced? As in, do you think that there's a lot more higher values, for example, instead of lower values, or vice versa? Do you think the distribution kind of seems a little bit symmetric or spread out? Do you think that the distribution is skewed? All this stuff is kind of important when we talk about data set shapes. So I guess a little discussion on what skewness is. So suppose we have some data. This is an example of a symmetric distribution. As you can see, it's pretty symmetric. It looks like the classic bell curve. The bell curve is actually a very important type of distribution that's used a lot in the real world. We also have something called left skewed and right skewed. So you might have less of some value here and then a lot up here. This is a skewed distribution. Here's another skewed distribution. So you can see like when you can see in one of these distributions, right? The tail is kind of pointing out right, and the other distribution, the tail is pointing out left. So we can talk about left skewed, I believe, here, and this is, I believe, a right skewed distribution. If I flipped it, I completely apologize, but you get the idea of what skewness is versus symmetric. So we can analyze the shape of the distribution, but we can also do a little bit better than just drawing a pretty picture to analyze, frequencies of your data points. We could even find the average, right? Or have an idea of how spread out our data is, right? Because that could speak a lot to, the problem at hand. So one type of statistic we could get is the mean, right? So the mean is just sum of all the numbers, divide by the total number of data points, right? So in this case, the mean would be 1 plus 2 plus 2 plus 4 plus 4 plus 4 plus 5. And we have 7 such data points, so we're going to divide by 7. So that's going to be, let's see, 4, 8, 12, 16. 16 plus 5 is 21. 22 over 7, right? So that looks like that's our mean. Another thing we can analyze is the variance. So this is just kind of like the spread of your data, right? So basically, what variance is we're going to take each data point, right? So we're going to call it a data point x. We're going to subtract it from the mean. We're going to square the difference, and we're going to sum up these differences, right? And we're going to divide by n minus 1, where n equals the number of data points, and that should get your variance. I can actually write it out too if that helps. So we have 1, 2, 2, 4, 4, 5. So we have 1, 2, 2, 4, 4, 4, 5. We have the mean as 22 sevenths, right? So I'm going to jot it down here, right? This is our mean. So what we are going to do is, for this row, right, we're going to take 1 minus 22 over 7. We're going to take the difference, and we're going to square it. And the reason why we square the difference is because we want to care about the spread of your data, right? So if your data is like very far left of the mean or very far right of the mean, we want to penalize both equally, right? Which is why we square the difference, right? Because when you square a positive number, we get a bigger positive number. When we square a very negative number, we get a very positive number, right? So that's why we square the difference when we're calculating variance. So likewise for this row, we're going to do 2 minus 22 sevenths. We're going to square that. And you can repeat for all these rows, right? So this will be, for example, here 5 minus 22 sevenths squared. And what I'm going to do is these differences I get, I'm going to sum all of this up, right? And when I sum all this up, let's say the number was, I don't know, like 61.67, right? It's not even calculated correctly. You guys can punch this into a calculator for yourself, right? But let's say this sum became 61.67. We're going to simply divide by the number of data points, which is 7, minus 1. So this will become your variance. And to get the standard deviation, we just take the square root of the variance, right? So standard deviation equals the square root of the variance, right? So just a couple of things to know. I would also add that the mean isn't the only way to get the average, right? One way you could get the average in a little bit more reliable way is what's called the median, right? So we sort our data in order right here from left to right, from smallest to largest, and we're going to basically take the middle number. So as you can see here, 4 is the middle number, right? Because there's 3 entries to the left, 3 entries to the right, and 4 is in the dead center. So 4 is our median. So why are we talking about mean versus median? Well, if you think about how the mean is just summing up all the numbers dividing by the total number of data points, suppose we had like, a data set of like 1s, 2s, 3s, 4s, and then you have like 100, 500. When you take the mean, these 100 and 500 like entries will cause your average to go really high, like it's skyrocketing basically, right? So in this case, the average we get from the mean is not necessarily reliable on like, our data set, right? But if we want to prevent such effect of large numbers, right, or extremely small numbers too, when calculating the average, we can use the median, right, and get a better idea of kind of the balance point or kind of the middle, right, to put it in easier terms. So that's just a quick spiel on what the mean versus the median is, and hopefully you kind of understand the idea of variance and standard deviation. I guess one way to depict variance is kind of just taking a look at some example histograms. So suppose we have like, I don't know, like, some data like here, right? And this point kind of is our center, right? As you can see in this histogram, right? We see a lot of points here, but we also have a lot of our data like really far out. So this is going to have pretty high like standard deviation. But if you had a data set where you have like kind of like a lot of values kind of in the center and then like, I don't know, not that many values out here, right? Out from the center, this is going to have lower variance, right? And you can see why, right? If you look at the data set below, right? The histogram shown here, right? This histogram right here is not very spread out, right? Although most of the data is concentrated in one spot. So you're not really going to have a lot spread. But this histogram up here, circled in green, this histogram right here seems more spread out visually, right? So you're going to have a higher variance in that case. So that's just an intuition of what the variance is. So hopefully that gives you a good idea of the mean and the variance. I will also add one more thing about the mean and the variance, so some properties, right? So for the mean, right? If you take your data, right, and add a constant to all points, right, the mean will increment by that constant, right? So for example, suppose you had 1, 2, 3 as your data, and I'm going to add 5 to all these points. You're going to have 6, 7, 8. So the mean of 1, 2, 3 is 1 plus 2 plus 3 divided by 3, which is 2, right? And the mean of 6 plus 7 plus 8 divided by 3 is going to be 21 divided by 3 is 7. So as you can see here, 2 plus 5 is 7. And notice we added 5 to all these data points. So the mean will increment by an additive constant you add to all your points. If you multiply your data by a constant to all points, right, the mean will actually multiply, will become multiplied by that constant. So what do I mean by this, right? So what I mean by this is if you had the data set 1, 2, 3, I'm going to triple everything, so you're going to have 3, 6, 9. So the mean of this is 2, the mean of 369 will be 18 divided by 3, which is 6. You see that 2 times 3 is 6, and we multiplied our data by 3. So that's why when we multiply by a constant, right, the mean will become multiplied by that constant. Now let's talk about variance, right? So if you multiply, if you add a constant to all your data points, right, how will the spread change? Does the spread just magically become larger or smaller when you shift all your data, like, by the same constant? So it's kind of like if I had a rectangle, right, and I move it here, right, do the dimensions of the rectangle necessarily change? Take a moment to think about that. Well, the rectangle doesn't just become bigger or smaller when you slide it over. Likewise, when you slide your data over, right, by adding constant to all your data points, the spread doesn't change, right? So variance is unaffected. Now let's consider the other side of the coin. If you multiply your data by a constant to all points, the variance gets multiplied. So let's take a look at an example, right? So when you see 1, 2, 3, the mean was 2, right? But let's get the variance real quick, right? So the variance is going to be 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared, right? Which is going to be 2. And we're going to divide this by 2 data point, 3 minus 1, which is 2. So the variance is 1, right? Now, let's suppose we multiply our data set by 3. So we have 3, 6, 9. So the mean is going to become 6. But let's see how our variance gets affected, right? So your variance is actually going to be 3 minus 6 squared plus 6 minus 6 squared plus 9 minus 6 squared, right? I'm just using the procedure we've talked about earlier, like when we calculated variance for this dummy data. So we see that the sum of the square differences will be 9 plus 0 plus 9, which is 18. And we're going to divide by 3. We have 3 data points, and we're going to divide by 3 minus 1, which is 9. So we noticed that the variance got multiplied by 9 when you multiply the data set by 3. So the variance actually gets multiplied by the square of the constant you multiplied. Now, how will the standard deviation change? The standard deviation will just simply get multiplied by the constant itself, right? So in this case, the variance of our data set originally is going to be 1. So the standard deviation is 1, right? Because the square root of 1 is 1. But when we look at the variance of the data set multiplied by 3, the standard deviation is actually 3. So when you multiply a data set by a constant, the variance gets multiplied by the square of that constant multiplier. So if you have a data set, you multiply it by 5, the variance gets multiplied by 25. But the standard deviation will get multiplied by 5. If you add, say, 1,000,000 to all your data points, the variance doesn't change. And so the standard deviation will remain unaffected as well, right? Because if the variance doesn't change, the standard deviation doesn't change as well. So hopefully that gives you some cool ideas about the properties of mean and variance from an intuitive standpoint. We're going to move on to the next section, which is random variables. So let's create a section here. So random variables, right? So what is a random variable from an intuitive standpoint? So here's kind of what it is, right? So we have events in space that happen, right? But wouldn't it be great to be able to like attach a number to something that happens? So for example, let's suppose we have the head and tails example, right? And I'm going to toss a coin. I'm going to toss this two-sided coin twice. What are all the outcomes I could get? Well, I can get 2 heads. I can get a head and a tails, a tail and a heads, and a tail and a tail, right? When I toss the two-sided fair coin twice, right? And that's because like 2 coin tosses are independent of each other, right? If the coin's fair, right? Because, the result I get from one coin toss doesn't affect the result I get from the next toss, right? So these are all the possible outcomes for tossing a fair coin twice. But here's what a random variable can do, right? Let's say I have these results of tossing a coin, but I want to know the number of heads, right? So I'm going to let x equal the number of heads, right? And what are the possible outcomes, right? What are the possible number of heads on tossing a coin twice? Well, you could get no heads, right? One head or two heads, right? So to get 0 heads, right, you needed to get 2 tails, right? Which is probability 1/4, right? Because we said that a coin toss is independent, so 1/2 times a half is a quarter. To get 1 heads, right, you needed to get HT or TH, right? Which is 1/2, right? Because 2 out of the 4 outcomes give you 1 head, right? To get 2 heads, you needed to get HH, which is probability 1/4. So what we've done here is we've taken this event outcome, right, of tossing a coin twice, and basically kind of quantified the importance, right? So if we had to make a table, right, we're going to let x equal the number of heads, right? And I'm going to do this, right? So x is going to have the following values: 0, 1, and 2, right? Because those are the possible number of heads we care about, right? And I'm going to have the probabilities, right? So in here, I would say the probability of getting 0 heads is a quarter. The probability of getting 1 head, right, will be 1/2, right? The probability of getting 2 heads is a quarter, right? So what we've done is we have converted this simple probability example in the context of a random variable problem, right? And random variables are really cool because we can essentially quantify like the significance of our outcome, right? It allows us to give us more interpretability, right, on events that happen in the real world, right? So what can we do with this table, right? Well, we can figure out something called expectation, right? This is just a fancy word for a mean, right? But this mean is a little different. And we can also get the variance of the random variable, right? But when we did mean earlier, we did it on just a given data set of numbers, right? So that definition is pretty easy, right, and intuitive. But in the case of expectation and variance, we have to account for the fact that not all points are equally likely to occur, right? Some values can occur more likely than others, right? So we have to account for that effect when we're figuring out an idea of our average and our spread, right? So let's talk about this definition, right? So the expectation is just a fancy word for weighted average, right? So you would take the number, so you would take the value of the random variable, right? Multiply by the corresponding probability, and add up those products, right? So we're going to have a little notation here, so it's okay like if you're a little bit confused, but I'll explain. So this symbol here, E of x, represents the expectation, right? Sorry if you can't read my handwriting. So this is the expectation, and we're going to call it like our quote-unquote average, right? And you probably have done weighted averages before. So like, for example, if you're in a class and your instructor says 80% of your grade is on exams and 20% of your grades are on homework, and if you know your average score on the exams and your average score on the homeworks, you simply like multiply the exam average you have by the weight of 80% plus the homework average times the 20% weighting on homework and add those together to figure out what's your overall grade. So you actually have done weighted averages before without really thinking about it, right? But let's look at the coin toss example to get the expectation of this random variable, right? So the expectation of the coin toss scenario, i.e. this table right here, right? Well, it's going to be 0 times 1/4, right? Plus 1 times a half plus 2 times a quarter, right? And on average, we see that the expectation here is 1. So on average, right, if I toss this coin twice and I do this a bunch of times, right, I'm expected to get 1 head, right? So in the long run, you're expected to get 1 head, right? Expected to get 1 head when tossing fair coin twice. At least a lot of times, right? So that's what the expectation is, right? Now, the variance is a little bit interesting, right? We call the variance of a random variable var x, right? And var x is going to be this crazy notation here, right? E of x minus ex squared, right? Now, I know this is a lot to digest, but let's go through it piece by piece, right? But before we get to that, let's take an aside to see what expectation is. So one way of writing this weighted sum is if you had like all the possible values of x in a random variable, right? Then we can say that e of x, and you'll see this a lot in the textbooks, it's just going to be the sum of x times p of x, right? So you take the one possible value of the random variable x, and you multiply it by the probability of such value occurring, right? So in this case, x would be the possible values of x in the coin toss example would be 0, 1, 2. The probabilities associated with x equals 0 is 1/4. The probability associated with x equals 1 is a half. The probability associated with x equals 2 is a quarter in the coin toss example. So this is just a summation notation, right? And we're going to find a way to express this variance in terms of a summation or in terms of something a little bit easier, right? So some basic properties of summation include the idea of constant multipliers and adding multiple things. So as a quick aside, if you're taking the summation of c times I, right, and you're going from I equals 0 to n, right, this is simply equivalent to c times the summation of I equals 0 to n of I, right? So when we have constants inside summations, we can essentially pull them out, right? If you have something like I plus I squared, for example, so if we have two things, like two separate functions, and we're summing the sum of those together, it's just going to become this. So we can actually kind of separate out our summations to make our problems a little easier. So essentially, you can distribute the summation over the addition, right, and subtraction. So these two things are equivalent. These two things are equivalent. So just some quick properties of summation. I'm going to make this in a different color so it's a lot easier for you guys to read. Okay, then we can distribute this, and it becomes that, right? So that's just some properties of summation. So I'm going to take advantage of a few properties here, right? So let's derive what the variance of x is to get a nice form. So let's expand this inside out. So we have we expand the polynomial out, so x squared, right? X here is our random variable, minus 2x e of x plus e of x squared. Now be careful when we're expanding out this last term of the polynomial, right? This e of x is a quantity that's being squared, so we have to write it like this, right? Now, the cool thing about expectation is because we have a summation, right? Expectation obeys a couple tricks, right? So when we have expectation of a sum of things, we can essentially split it up, right? So this thing will become e of x squared minus e of 2x ex. Let me actually turn this into a plus, and then we'll see. And we're going to do e of ex squared, right? All right, so so the expectation of x squared, right? We can't really do anything here, right? But by definition, this is just simply x squared times p of x, right? So that part stays as is. But what do we notice here? We have a constant multiplier, right? And if we recall our property of summation, right, when we have a constant multiplier inside of some, we can pull the constant out. So in this case, the constant multiplier is -2. So this term here will become -2 e of x e of x, right? But what do we notice here? When we calculate the expectation, are we getting a variable or are we getting a number? Well, when we look at our definition of expectation, right, we have a finite set of values of a random variable and we have probabilities associated with it, right? So when we take this weighted sum, right, we're guaranteed to get a number, right? If you think about how we calculate the weighted average, like, for a grade, right? Given, say, 80% of your grades on exams, 20% on homeworks, and your exam average and your homework average. you essentially multiply the corresponding like weights with the corresponding averages and add those together. And you get one number, which represents your final grade, right? So in this case, expectation, or this term here, is secretly saying that I'm a number, right? So remember when we have constant multipliers and summations, we simply can pull it out, right? So this here becomes -2 expectation, and then we have an x that is left inside, right? So that's what this term is going to be. Now right here, right, we know that expectation is a number. So is the square of something that's a number a number? Well, it is, right? So if my average was say 7, well 7 squared is also going to be a number, and it's actually a constant, right? So when we take the expectation of constants, um, the expectation of just a constant is just a constant itself, right? So if I have expectation of 7, the expectation of 7 is just 7, right? Like we can only get 7 like forever, right? And nothing else. So it's kind of a really boring distribution. So the expectation of just a constant is just a constant itself. So the expectation of the square of the expectation is just going to be expectation squared, right? Now we can simply add this to this to this, right? And we notice that the expectation times the expectation is just the square, right? So we have expectation of x squared minus 2 expectation squared plus expectation squared, right? So we find this. The variance associated with the random variable x is simply this. So this is a handy dandy formula you're going to want to know. So I would recommend you have this kind of, in your notes somehow. So this is the handy dandy formula for how to get the variance of a random variable, right? Using your properties of expectation, right? So let's make this a little more concrete through an example, right? So let's suppose we have this table, right? So I have a random variable x, and the possible values are 10, 20, and 30, right? And the probability of getting a 10, 20, or 30 are going to be as follows, right? So it's going to be a half, a quarter, maybe it's going to be a third plus a sixth, right? To make the numbers a little more interesting, right? Actually, I'm going to, yeah. So we have 1/2, a third, and a sixth. Let's make sure these probabilities sum to 1. That way it's a valid distribution. So 1/2 plus a third, that's going to be 5/6, plus 1/6 is 1. So all the probabilities sum to 1. So what are we going to do here? Let's find expectation of x. And then we're also going to find the variance associated with x, right? And then we're going to do something a little bit fun at the end, right? So let's find the expectation of this random variable with this table, right? So the expectation is going to be 10 multiplied by a half. We're essentially taking the weighted sum plus 20 multiplied by the third plus 30 multiplied by a sixth, right? We're multiplying essentially the value of the random variable to its corresponding probability to get a better idea of our average, right? Or long-term like gain. So 10 times a half is 5, 20 times a third is 20 thirds, 30 times a sixth is 5. So we have 5 plus 20 thirds plus 5. And that's going to be simply equal to 50 thirds, right? 10 plus 20 thirds should be 50 thirds. Yeah, so that will be our expectation. Now let's get the variance of the random variable, right? But what do we notice? Let's use our trick here. We're going to do this instead to get our variance, right? We're going to use this formula. So we have to find expectation of x squared, right? So what is this going to be? Well, we have to square each of these x values here and multiply by these probabilities, right? So we're going to have 10 squared times a half plus 20 squared times a third plus 30 squared times a sixth, right? So the expectation of x squared in this case will be 50 plus 400 thirds plus 150. So this is going to be 200 plus 400 thirds, which is going to be 1,000 over 3, right? So 1,000 thirds, right? And we have found our expectation right here from earlier, right? We found that it was 50 thirds. So to get the variance of x, it's just simply 1,000 thirds minus 50 over 3 whole squared. And you can just punch this into your calculator, but this is the variance associated with your random variable, right? Now let's do something a little bit more fun, right? Some cool properties to know. The properties of variance still remain the same. So if I add, let's say 5 to, this random variable, right? So the 10 becomes a 15, the 20 becomes a 25, the 30 becomes a 35. And we compute the variance associated with x, given the shift. We'll see that the variance won't change actually, because the expectation is going to change accordingly, right? Because when we shift our data like by a constant additive factor, the variance or the spread doesn't really change, right? So we will actually see that the variance of, random variable plus a additive constant, right? It's not really going to do anything, right? At the end of the day, right? So you're not really going to have a change in your variance. However, if you have the variance of a constant multiplier times a random variable, so suppose we multiply, the 10 by 2, the 20 by 2, and 30 by 2, the variance will actually quadruple, just like we saw earlier, right? So if you look at the example we did right here, right? When we took the data set and multiplied it by 3, we compared what the variances were like. So when you multiply, the data set by a constant multiplier, the variance will be multiplied by the square of that multiplier. So likewise, it'll happen here too. And expectation, similar rules apply. So when you're adding a additive factor to your x, the expectation will shift accordingly, right? And when you multiply this data set, the 10, 20, and 30 by, say, 5, right, the expectation will also get multiplied by 5. So you'll actually see, like, these properties still apply for expectation and variance of a random variable. So that's kind of the gist of what you need to know to find expectation variance. Let's do another fun example using this data set, right? Or this table. So let's say I knew expectation of x, and I'm going to do something a little interesting. What if I want to do this? What if I want to find the expectation of 2x plus 1 squared? So say my x were these values, just like from earlier, right? I'm going to create a random variable y by simply multiplying the x by 2, adding 1, and then squaring it. Now, what's the expectation going to be? Well, what we're going to do is expand out the inside, right? So it's going to be the expectation of 4x squared plus 4x plus 1. And if you recall our properties of expectation, right, we can actually separate these terms out, right? So this is going to be equal to expectation of 4x squared plus expectation of 4x plus the expectation of 1, right? So the expectation of 4x squared, we can actually pull constant multipliers out. So this is going to become 4 expectation of x squared plus this term is going to become 4 times the expectation of x, right? Because we can pull constant multipliers out, right? So what we did here from this step to this step is to essentially separate out these terms, separate out this term, this term, and this term in their own expectations, right? These are properties of summation notation. And for each of these terms, we're going to handle them separately. So when we have constant multipliers, let's pull them out to make our lives easier. We also have here the expectation of a constant, right? So the expectation of a constant is just the constant itself. So this is going to be a 1, basically. So what is the expectation of x squared, given what we found earlier? We have actually found the expectation of x squared. It's just this 1,000 over 3. So we're going to substitute that in. So it's going to be 4 times 1,000 over 3. And what is expectation that we found earlier? Well, we've already done it here, right? It's actually 50 over 3. We've actually found it. So we can substitute. And then we're going to add 1. So whatever this result is, this will become the expectation of 2x plus 1 quantity squared. So that is how you can use expectations you've already found or variances you have found to find what you want. Now, let's do a little bit of an interesting problem, right? Here's another quick interesting problem that I find. So let's suppose the following, right? Suppose we know the following information about a random variable x, right? We know that the expectation associated with this random variable is going to be 5, and we also know that the variance is 3, right? Given this knowledge, let's compute the following expectation, right? So let's compute this expectation, right? Given this knowledge. So what do we do first? Let's figure out what we need to evaluate here, right? So the expectation of 4x minus 3 squared is going to be the expectation of 16x squared minus 24x plus 9. We're just expanding out the polynomial, right? And then, as you can recall from what we did earlier, we're going to essentially distribute the expectation over and separate out this term, and this term, right? So what do we have now, right? This is going to become the expectation of 16x squared, right? Plus the expectation of negative 24x plus the expectation of 9, right? Now, what do we have left to find, right? Well, let's actually pull out the constant multipliers right now. So we have 16 expectation of x squared minus 24 expectation of x. We also know the expectation of a constant is just the constant itself, so expectation of 9 just becomes 9. Now, what do we have left to find? We have to find these two values. Well, let's look at what we're given. We know here that the expectation is 5. So we can essentially substitute 5 here, right? But we have to still find this term right here. What do we do? Let's take advantage of our second given. We know the variance, right? What do we know about variance? We know that the variance of x is simply the expectation of x squared minus the, let me just put this let me just put this somewhere else. So we know that the variance, right, associated with x is equal to the expectation of x squared minus the expectation squared, right? This is from the identity we have proved earlier, right? So we're just trying to exploit that fact. Yeah, just trying to make this a little bit legible here. Okay, what do we know about variance x? Well, we know that the variance is 3, right? So we can plug 3 on this side of the equation. We want to find expectation of x squared, so we don't have that. Well, we do know expectation, right, of x. It's actually 5. So minus 5 squared. So we find here that the expectation of x squared, right, is just 28. So now that we know expectation of x squared, all we have to do is plug 28 here, and now you have all the information you need to essentially evaluate this quantity, right? It's just going to become this. So you can just plug this into a calculator and you'll get the answer for that. So that takes care of expectation and variance, and basically the key is knowing how to use the identities you know and the basic properties of expectation. The properties we were talking about in terms of separating out the terms within an expectation and pulling out constant multipliers. This is called the linearity condition of expectation. You don't really have to know that word, but it's just kind of a fun fact. So that wraps it up in terms of how to do expectation and variance problems of random variables. Hopefully this video kind of gives you a nice comprehensive review on what a random variable is and how you can convert event spaces into random variables to help make analyzing your problem a lot easier. So thank you for tuning in, and hopefully I'll see you in the next video. Have a good rest of your day.